let's move on to second order. So I know I've been talking for about 25 minutes already. This is kind of a big lecture because we're going through these models and we're getting into the meat of this. Okay. So now the first one that I'm going to go to here is talking about just the basics. So if we were to talk about a very simple second, not actually not a simple one. For some reason I'm doing the more complicated one first. A plus B goes to C. Okay. And if I were to write a rate law for this, some of those rate laws would look like the following. It would be dA by dt, and I'm going to put the negative sign in front of there, right, to get that stoichiometric coefficient correct. And I know that that's going to be the same as negative dB by dt, okay, which I also know is going to be the same thing as positive dC by dt, and all of that is going to equal k times A times B. First order in A, first order in B, second order overall. All right? And so I've got that set up here in the Mathematica model. And if we follow through that here real quick, check it out. Look, I've got A prime of t, so we know that's dA by dt, equals negative k times A times B. All right? So that's all good. So now we've got to write the rate for B. Okay? dB dt equals negative k times A times B. So it's the same thing. And then now finally, dC dt equals positive k times A times B. Okay? And then for this model, so this is model 4, by the way. And you don't have to do a 4A and a 4B. So this is, again, my little extra to show you what's going on with second order reactions. So in here I set up A and B to be slightly different concentrations so that you could actually see them. If I were to put A and B as the same concentration, if they both started at 0.05, then it would just look like one curve on this graph, okay? And so now if you follow along here, look, we're solving our model for A, B, and C now, okay? And when I do this plot evaluate code, I have to evaluate it for A at time t, B at time t, C at time t, and then I replace it with this model for A, all right? So now this is a second order reaction, and if you've got a really good eye, you might pick up that these are exponential decays. And that is correct, okay? So in this second order reaction with A plus B, right, the profile of A, when I solve this differential, okay, will actually be A at time t equals A0 e to the negative kt. And this one, B, it is still first order just in B, okay? So it will also have that exponential decay. And C, of course, will be the positive of that, right? C will be it won't be to the negative kt. We'll work out what the product rate law turns out to be later. It turns out to be 1 minus e to the minus kt. Okay, but we'll work that out later on, because right now it's really just all about the reactants. And the Mathematica model is working out these for us. Okay, so there's exponential decays here. All right, and so what if now, instead of thinking it like this, because actually we can't even solve this by hand. If I were to now go through and try to solve this in the same way that I did up here, solving these differentials, right? This becomes exceedingly difficult. The Atkins has the full solution of doing that, and you basically arrive that each individual reactant has a first order decay because they are first order in each reactant. So now what if we had a second order reaction that looked more like this? A plus A goes to B, okay? Or in other words, so I'm going to separate here. What if we had 2A goes to B with rate constant K? So first order in A, first order in A, so it's a second order reaction overall. And so now what that means is I can write negative dA by dt equals K times A squared. Okay? So now when I go to solve this thing, all right, so this one we can solve, no problem, okay? So when I go to solve it, it's going to be the integral, still same way we did it before, a0 and a at time t, and dA over a, all right? And let's see, I'm going to keep the negative sign here. You'll see why for it makes the solutions a little bit easier. Oops, I wrote it completely crazy in my notes here. It's dA over a squared, and that's kt, okay? And so when I go to solve this thing, what I end up getting is the following. 1 over at minus 1 over a0 equals, oh, that's k dt, right? Integrated from 0 to t. And so then now that all equals kt. And so rearranging now, if I plot 1 over at, that's 1 over at equals kt plus 1 over a0. And this is the linear form of the integrated rate law, where this is now y equals mx plus b. All right? And so what I should get out of a second order reaction with only one reactant, okay? When I plot now, let's see here. If I plot 1 over the concentration versus time, look, there's a positive number there. The intercept is 1 over A initial, okay? So it's not going to start at 0. It's going to start at some value, right? And it's actually going to go up, okay? And so my slope is still equal to K. And we should also, while we're here, let's actually work out the units of K just really quick, okay? So let's see here. I'm just going to give them to you instead of working this out, all right? So K for a second order reaction has to be liters over moles per second, or for our gas phase, cubic centimeter per molecule per second. So the units on first order versus second order reactions are different, and we have to pay attention to that. Okay, so here's what I got going on in my Mathematica model to really highlight these two differences. When you have a reaction that's let me go back up here. Yes, first order in each reactant, A plus B, right? So I noted here, you get an exponential decay. But if you don't believe me, if you're looking at this and you're like, well, that could still be a 1 over concentration, it could. I don't have good enough eyes to tell that that's exponential. So what I did here is I created a manipulate model the same way I did above. And I'm manipulating the rate constant. And the reason why I'm manipulating the rate constant is because it really shows you the test, okay? And my test is, look, when I plot 1 over concentration, which I also adjusted in this model, and I did that by saying evaluate 1 over the concentration, okay? These should be a straight line with a positive slope. I see a positive slope, that's good. But look, as I manipulate this rate constant, that really shows you that this is not making a straight line. And so notice I'm plotting A and B here, and A and B are my reactants. I left off C on this manipulate model. But you can see here that this reaction, even though it's second order, it is not second order in A or B. It's first order in A or B. So technically, if I plotted the natural log of concentration versus time on this, now my A and B would have negative straight line slopes, okay? And then to prove that to you, I made a new model, which again, you don't have to do, model 4B, just second order in one reactant, right? A plus A, okay? So I just solved it for A and B, and when you look at this, you might think, well, that kind of looks like an exponential decay, and it does, right? My eyeballs aren't good enough to just look at that and know it's exponential. However, what I can do is test it. And I'm going to test it by, once again, evaluating 1 over the concentration, because if I plot 1 over concentration versus time and I get that positive slope straight line, then it's definitely a second order reaction, and it's a second order reaction in one reactant. So here we go. So you can see already that's looking pretty good. And when I manipulate the K here to make it bigger, look at all of those values of K, it just remains to be a straight line. So it's definitely passing the test that this is a second order reaction. Okay? Second order in one reactant. With this A plus B situation, that can still most definitely be a second order reaction. However, it's first order in one reactant and first order in another reactant. Okay.